Hello and welcome. I'm Dr. Syed Mostafa Safavi, and you're listening to our podcast series on deep learning for intrusion detection. In this series, we explore how cutting-edge AI techniques are reshaping the way we detect and respond to cybersecurity threats. This podcast is produced with the valuable support of Alicia Tan, who has been instrumental in coordinating and preparing each episode. Now, let's get started and dive into today's topic. Welcome, everyone. Today, we're diving deep into a fascinating set of topics, from deep learning for intrusion detection to the intricate world of graphics pipelines and parallel processing. Let's jump right in.
I'm all in for this discussion. So what stands out first in this mix of content?
Well, it starts off with a nod to deep learning for intrusion detection, a critical application. But then it shifts gears into exploring the architecture of graphics processing. It's like, connecting the dots between algorithmic data parallelism and how GPUs efficiently handle enormous amounts of tiny computation.
Yeah, right. It's almost like setting a stage where two heavyweight topics, security through deep learning and visual processing through GPUs, intersect.
Exactly. And on the graphics side, we see the fundamental breakdown of the pipeline. Think about it. A transformation phase that converts 3D world space into image space per vertex lighting, and then the rasterizer comes in converting geometric data into a stream of pixels, right?
Absolutely. The rasterization process, with all its interpolation and mapping of per vertex data across pixels, is like the magic behind converting abstract models into beautiful visuals.
And then comes shading. The fragment processor computes final pixel colors, sometimes even reads textures. It's kind of similar to how deep learning processes can be seen as repeated, short, iterative algorithms that refine outputs over large data sets.
Right, so it's a bit like comparing pixels in a game to neurons in a deep learning model, each doing its little part in parallel calculations.
Oh, absolutely. It's like, handshakes between millions of vertices or pixels. Each operation is relatively lightweight, but repeated millions of times. And that's why we call it embarrassingly parallel.
Yeah, that phrase always cracks me up. Embarrassingly parallel. But it really nails the idea that these tasks can be massively subdivided, right?
Right, so moving on, the content then delves into pre-GPU graphics cards, which were essentially dedicated accelerators. These were special-purpose, ultra-parallel systems, like the Voodoo chipset era in the late 90s.
Exactly. It's crazy to think how far we've come. From custom cards to now integrated GPU solutions in almost every device we use.
Yes, and then we hit the big breakthrough, NVIDIA CUDA. This introduced the idea of SIMT, single instruction, multiple threads, which essentially marries the idea of executing one operation simultaneously but across many threads.
SIMT is pretty revolutionary. It combines features of VLIW, superscalar, and SIMD architectures to maximize throughput on large data sets, doesn't it?
Right. It's like, imagine having one command that tells thousands of little assistants to do the same task at the exact same moment. It's a game changer in data parallelism.
Yeah, but I would respectfully question a bit. Does this model have downsides, say, when dealing with tasks that aren't so parallelizable?
Great point. And that's where the whole CPU and GPU dichotomy and Amdahl's law comes in. CPUs, with their ability to handle lower latency serial tasks, can outperform GPUs on work that is inherently sequential.
True. So it's really about choosing the right tool for each part of the workload, splitting the job intelligently between a CPU and a GPU.
Exactly. And this conversation also covers how dual-phase programs work, handling the sequential parts on the CPU and the brute force, massively parallel parts on the GPU. It's like a tag team for computing.
Right. This reminds me of how deep learning, especially for things like intrusion detection, often leverages GPUs for training on huge amounts of data, while the CPU handles the orchestration.
Yeah, the same principle applies. Speaking of deep learning and computational grids, another interesting bit is mapping computations to grids. Whether it's matrix algebra, image processing, or physical simulations, many operations seamlessly map to these grid-like patterns that GPUs excel at.
And that's where frameworks like OpenCL play a role, right? Providing a bridge to run these computation-intensive tasks across heterogeneous platforms, from GPUs to even FPGAs.
Absolutely. OpenCL opens up the idea that you can use a portable language to tap into multiple hardware types, which ensures that these environments aren't locked to NVIDIA GPUs alone.
Right on. But then there's also PLAD-ML, which seems to be a sort of tensor compiler that aims to make deep learning feasible on less standard hardware, like laptops or even embedded devices.
Yes, PLAD-ML is like the universal translator for deep learning hardware. It bridges the gap between high-level deep learning descriptions, like convolutions, and the underlying specifics of each chip.
Yeah, exactly. I find it quite fascinating that these solutions tackle the issue of licensing restrictions and limited hardware support, making deep learning more accessible and portable.
Definitely. And bringing it back to GPUs, the evolution in architectures from NVIDIA's Volta with its massive core counts through to Ampere with ray tracing cores really highlights how the computing paradigm is shifting more and more towards parallelism at a scale we never thought possible before.
Yeah, and speaking of architectures, the detailed breakdown of Volta shows, for instance, 84 streaming multiprocessors with thousands of cores split between INT32, FP32, FP64, and even tensor cores. That's a lot of parallel oomph.
Right, it's like, imagine having a workforce of thousands specialized in different skill sets. Address calculations handled by INT32 cores, and the heavy lifting of floating point math by FP32 cores, all happening simultaneously.
Yeah, and I noticed that each iteration in a pipeline loop can perform pointer arithmetic and then process data concurrently. It's pretty clever how they keep the execution pipeline full.
Yeah, it's almost synchronizing different lanes of a highway where each car plays its part without causing a traffic jam. The simultaneous execution is optimized to ensure there's no idle time in the GPU pipeline.
Right. Now coming back to the bigger picture, how do you see these graphic pipeline principles affecting deep learning, especially in a security context like intrusion detection?
Well, it's intriguing. The idea is that both domains rely heavily on processing huge amounts of independent data concurrently. In graphics, it's pixels and vertices. In deep learning, it's feature vectors and signals that might indicate an intrusion.
So in other words, the data parallelism that drives graphics acceleration can be leveraged to handle complex AI computations.
Exactly. And the concept of mapping non-grid streams to grids further extends the application, allowing even non-conventional data types to benefit from these parallelization strategies.
Right, that's pretty revolutionary, because it means that advancements in GPU technology directly benefit areas like deep learning for intrusion detection, by speeding up the detection processes almost in real time.
Yep. And it also stresses the importance of carefully partitioning workloads when using heterogeneous systems. The dependency graphs shown in the content highlight how a programmer must decide what goes to the CPU and what cascades into the GPU for optimal performance.
And that balancing act is crucial. If you were to, say, send too much sequential work to the GPU, you'd be underutilizing its parallel capabilities, which then falls back to what Amdahl's law predicts, a bottleneck effect.
Exactly. And that's where the art of programming comes in. You need to finely tune which tasks benefit from parallelization and which should remain serial. It's definitely not a one-size-fits-all approach.
Yes, indeed. So, wrapping it all up, the content really paints a picture of how the evolution from simple accelerators to modern GPUs has not only empowered graphics rendering, but also revolutionized high-performance computing in deep learning contexts.
Absolutely. It's a thrilling journey from the early days of 3D accelerator cards to the sophisticated CUDA and OpenCL ecosystems we have today, each step building on the idea of better, faster, and more efficient processing.
And as we see, whether you're tackling visual graphics or complex security challenges in deep learning, the principles of parallel processing lay the foundation for what comes next in technology.
Exactly. Thanks for this engaging discussion. It's been a ride covering everything from vertex shaders to tensor compilers. Until next time, keep exploring the magic behind the data.